Hi there, welcome back. Once again, we are dealing with survival analysis. In this lesson, I would like to introduce another class of models that we can use to estimate the survival function of a random variable, and this class goes under the name of accelerated failure time models. In the second part of this online lesson, we will then consider a sort of procedure to correctly build a survival model from the very beginning to the end. That is to say, when we want to test its goodness of fit. Naturally, in this class, I will be quite general. More details are on the course platform as usual. Accelerated failure time models are a family of essentially parametric models that start from the consideration that the random variable capital T cannot be negative. This is true both when capital T represents time, but also under other specifications. You will find more details on the course platform when we deal with LGD. Now, since t cannot be negative, we can work with its logarithm. In practice, we assume that the log of t follows a linear model, and for every single counterparty I, we have that log of ti is the sum of two elements, xi prime beta, where we have the different covariates and their coefficients, and an error term epsilon I. This is the element on which we will make our parametric assumptions, our parametric choices. In particular, changing the distribution of the error term, we can obtain very different models. Typically, we assume this error term to have mean 0 and standard deviation 1, but this assumption can be somehow relaxed. In other words, we have that in an accelerated failure time model, the distribution of the log survival is just a simple shift of the baseline distribution of the error term. By exponentiating, we obtain the following representation, where the error term is now substituted by the exponentiated error term, Ti0. Why do we call these models accelerated failure time models? Just have a look at the following example. Consider two types of companies, such that we can give the following two AFT representations. Now notice that in both cases the exponential terms x of x prime beta is nothing more than a multiplicative term for the exponentiated error terms represented by the capital T's, T1, 0 and T2, 0. And remember that the error term is exactly the object on which we make our parametric choices. Now, if we assume that the multiplicative term of the companies of type 2 is 2 times the one for the companies of type 1, essentially we are saying that the default time of a company of type 1 is half of that of a company of type 2. It's like we have accelerated the lifetime of companies of type 1. AFT models are typically easier to estimate than proportional hazard models, but they are also less flexible. The estimation of accelerated failure time models is performed using generalized linear models. Naturally, the actual model we are estimating depends on our parametric assumptions on the error terms. For example, if we assume normally distributed error terms, what we are dealing with is nothing more than a log normal regression. Why log normal? Because the normally distributed error terms are affecting the log of t. Now, in the case of no censoring, AFT are easily estimated, and it's really the use of generalized linear models. Most problems arise when we are considering censored observations. In that case, depending on the parametric assumptions, it can be difficult to obtain the parameters of the model. In the case of normally distributed errors, this is not a big deal because we can rely on the so-called Tobit regression, which is quite common in economics. A quite general and interesting model is the one we obtain by assuming that the error terms follow a so-called extreme value distribution. You can see the CDF on your screen. Please notice that in this case mu and sigma are not the mu and sigma of a normal distribution. We are not speaking about the mean and the standard deviation, but mu is known as location parameter and sigma is the so-called scale parameter. For what concerns psi, psi is the shape parameter, that is to say the parameter governing the tail of the extreme value distribution and also governing the possibility, the probability of extreme events. Now, if we assume errors to be EVD distributed, what we have, we can generate a lot of different linear models depending on the parameters of the extreme value distribution, which is actually a family of distributions. We can obtain exponential regression, we can obtain Weibull regression, log logistic regression, and so on. Now, assume that we have in mind a model that we want to estimate on actual data. This model can be whatever type of model, can be a proportional hazard model, can be an AFT, other types of models, is not important. The procedure we are going to see, it's always the same. In the last minutes of this class, I want to share with you some steps that we should follow in order to obtain a satisfactory model, a model that can be reliable and that we can trust when making our evaluations and predictions. A first simple but fundamental and very often underestimated step is to verify if the basic assumptions of our model are satisfied. This can be done using graphical and heuristical tools. Now, assume for example that we think that our data somehow follow a proportional hazard model with Weibull intensity. Why don't we use a Weibull plot just to check if the basic assumptions are satisfied or not? Remember that estimating a given model on the wrong data is totally useless, if not dangerous. We can then estimate our model. We will obtain a series of estimates with their standard errors, their p-values, their critical values. What we have to do is to remove the not significant quantities. It is very important to remove the not significant covariates, that is to say those whose parameters are not significant, one by one and not all together. This is due to the fact that sometimes two covariates may share the same information, so removing one of them can make the other one significant. At a certain point we will remain with all covariates that are significant. Should we stop here? In reality, no. It would be nice to see if we can still remove some of the covariates, some of the surviving covariates, or if we can aggregate them in some way. Why? Because we are looking for a model which is good in terms of fitting, but that is also parsimonious, that is to say without too many covariates, without too many parameters. We want something which is strong and simple. Using model selection, that is to say relying on quantities like the archaic information criterion, the BIC and the likelihood ratio, we can decide if one of the significant covariates can be safely removed or not from the model. Typically, we compare the model with the covariate and the model without the covariate, and looking, for example, at the archaic criterion, we see which of the two has the best value for the criterion, and we choose that one. After removing all the covariates we can remove, we can come back and try to add new covariates. Typically, we can look for interactions by adding the product of two or more covariates. In order to select the best model, again, we use selection procedures based on the archaic criterion and so on. At a certain point, we hope we will obtain the best parsimonious model. What we have to do is to test its goodness of fit by comparing the estimated survival function we obtain from the model with the empirical one. And typically we can approximate the empirical one using the Kaplan-Meier estimator. Now, we can do this comparison visually or, to be more rigorous, using goodness of fit procedures like, for example, the Kolmogorov-Smirnov test. As I told you before, on the course platform you will find extra materials on the things we have been discussing together in this video lesson. For the moment I stop here. Thank you for your attention. Goodbye.